Next question. If F is a continuous mapping of a metric space like X into another metric space like Y, prove that the image of the closure of E under F is included in the closure of the image of E under F. So recall that. Let's just write down the short recall here for you. The closure of a set is defined as the set union with its E prime, where E prime is the set of all limit points of E. Very good. Let us begin. We want to show that this set is a subset of another set. To show that A is a subset of B, we need to show that for any element in the smaller set, that element lands in the bigger set. Very well. Let us take some random elements in the first set and show that that element lands in the second set. Let X belongs to the closure of E. Or f of X belongs to f of the closure of E. We need to show that this is our goal. We want to show that f of X belongs to the closure of the image of E under F. Let's put a question mark here. If we can show that f of X is a limit point, then we're done. So remember the definition of the limit point. A point like P is called a limit point of set E if every neighborhood of P contains some other points like Q, which is not the same as P, and this Q belongs to set E. So let us take a neighborhood of f of X. Suppose O is a neighborhood of f of X. If we can show that this neighborhood contains any other point in f of E, then we're done. Let us use the fact that f is continuous. Since f is continuous, then the inverse image of O contains a neighborhood of X. Why is that? Take a look at the following. Let me put that in parentheses for you. Since an open ball with radius epsilon, small radius, and center at f of x is going to be contained in O, because O is a neighborhood of f of x, and we can always find a smaller ball with center f of x and with a very small radius like epsilon contains in O. By continuity, we can find a positive delta such that f of the neighborhood with radius delta at x be contained in the open ball with center f of x and radius epsilon. Therefore, the neighborhood including x is going to be contained in inverse image of O. This guy is included in open set O. So inverse image of O is a neighborhood of x. Very good. Let us continue. Since we assume that x belongs to the closure of E, there is a point like U of E such that U belongs to inverse image of O. Where does it come from? It comes from the definition of closure. The closure includes the set union with its limit points. And based on the definition of a limit point, any neighborhood contains another point which belongs to that set itself. So what does it tell us? It tells us, well, f of u belongs to O, also belongs to f of E, belongs to the intersection. Since O is any neighborhood of f of x, therefore we can conclude that f of x belongs to the closure of f of